Okay, let's have a look at this next topic, which is expressing numbers as powers of the same base. Now, this works for a whole lot of different contexts, but the most basic of all is if you've got any number, and let's say the number is, I don't know, 20, and it's 20 to the power of x. As long as we keep the power the same, we can break the base up into its component factors. So you could write that as, and we know that 20, for example, is 2 times 10. But if it's that, we're going to put an x here and an x here, and it's still true because 2 tens are 20. We keep the power the same. Well, let's break it up even further, because we know that 10 is 2 times 5, so I could write 2x times 2x times 5x, because 2 times 5 is 10, and 2 times 10 is 20. In other words, 2 times 2 times 5 is 20. If that's the power of x, these must also all be to the power of x, and it's true. Let's have a look at another example. Let's say I take the square root of 56. Well, that's equal to the square root of, well, we know that 7 times 8 is 56. And this is also true. And it's not sure to go 7 times 8, find the square root, and you've got exactly the same thing as the root of 56. Of course, I could write it out into little bits, and you can see why this is true, because there's actually a power going on here. 56 just means, root 56 means 56 to the power of half, which is the same as 7 to the power of a half, times 8 to the power of 1/2. The fact that 56 is 7 times 8, and this is to the power of a half, only works if this is to the power of half, and this is to the power of half. Of course, 8 is also 2 times 2 times 2. So you could rewrite this as 7 to the power of a half times 2 times 2 times 2, as long as you make all of these to the power of 1/2. And that all works. So this is what we mean by bases. Bases we can move the base around by finding its component factors, as long as we keep the power, the index, the same. So let's say you have a multiple index, a multiple term index, sorry. So let's say, for example, you had, let's say 8. And let's say this was the power of x plus 1. Well, this is the same, of course, as saying 2 times 2 times 2. Because 2 times 2 times 2 is 8, but we now got to keep that index the same. It's going to be x plus 1, x plus 1, x plus 1, x plus 1. And of course, now it's of course still true. But now we can do something else, which is rather useful. We keep the base the same. Here it is. Because when you're multiplying numbers with the same base, oh, wait, sorry, I've got a 2 in there. What am I doing? Hang on. What? 8's 2 times 2 times 2. So we've got too many. Crikey. Not good. My bad. See, I'm so intent on getting to the next line. I can't see what I've just done. I'm looking ahead. I'm thinking ahead. It's not good. It's not a great place to be. I'm so sorry. Okay, so we keep the base the same. We can just add the powers. And we know this because, let's say, and I'll make a little sidebar over here, if you've got x squared times x to the 4 times x to the 6, bases are the same, and we can just add the powers. So we know, of course, that's x to the power of 6, and 4 is 10, and 2 is 12. I'm just adding the powers. But the same thing is here true as well. So the bases are the same. I can just add the powers. So this is x plus 1, x plus 1, x plus 1. Now I could write that as 3 lots of x plus 1. Or if you're a bit of a glutton for punishment, you could go to x plus 1 plus x plus 1 plus x plus 1. Either way, excuse me, you end up 3 times x is 3x. And 3 times 1 is 3. So it would be true to say that 8 to the power of x plus 1 is the same as 2 to the 3x plus 3. And that's what we do. That's what we're manipulating when we're expressing numbers as powers of the same base. And knowing how to extract or extrapolate different combinations allows you to combine numbers in various ways. And you'll see that in the next example.